You are welcome to the GMAETS 41's live class today. In this class, we are going to give attention to ordinary differential equation, ODE. For our dear friends in Unizik, because this course is coded Math 202. In our previous class, in this course, I had already taught you the concept of type 2 form of first order ordinary differential equation. You recall that I taught you how to identify first order ordinary differential equation, the types that are separable variable in nature, that is the type in which the variables can be separated before you integrate. I also went ahead to teach you how you can solve such equations, how you can solve them. Okay, of course, you have to separate the variable and then you integrate as required. So in this class, I'll be teaching you type 3 of first order ordinary differential equation. Please take note. Our first order ordinary differential equation, FOODE, I have decided to be using the acronym FODE for it. So whenever I pronounce, FODE, then know that we are referring to first order ordinary differential equation. So in this class, we shall be giving attention to homogeneous first order ordinary differential equation. That is what I'll be teaching you. So the focus of this class first would be, how to identify first order differential equation that is homogeneous. How to identify it. That's one of the focus of this class. And then secondly, how you can actually, the formula per se or the approach, I can call it the transformation that you use, okay? The transformation you use to reduce a separable variable, to reduce a homogeneous FODE to a separable variable FODE. You get that right? I take that once again. We are going to focus on one, how to identify a homogeneous first order ordinary differential equation. And then secondly, we're going to learn about the transformation we use to reduce this separable variable, to reduce this homogeneous equation to separable variable equation. So two key things that you're going to learn from this class today. And of course, as usual, once you connect to this class, share the link to this live class to your departmental WhatsApp group, to your friends, to your classmates. If you're connecting to this class from wherever you are joining the class from, you can indicate, just tell us where you're connecting to the class from. So that is much of the things you should know about what we are going to deal with in this class. Because in our next class, we shall be looking at how to solve a homogeneous FODE problem. All right. Remember, like I told you, when you're dealing with ODE, the first thing you have to do is to be able to identify the form of or the type of ODE, first order ODE you're dealing with. Okay. So I am going to write this for you. The general form of homogeneous equation. General form of homogeneous first order ordinary differential equation. It takes the form f of x comma y, and then f of x comma y dx, now have plus g of x comma y, and then dy. We make this equal to 0, such that either one of the differential coefficient part, either one of the differential coefficient parts. Okay, let me just go straight. Either one of dx or dy, or both dx and dy. have, the variables added or subtracted, variables added or subtracted, and the degree in the x and dy, are equal. So this is how you identify a homogeneous first order ordinary differential equation. This part is very, very important. Degree in dx and dy are equal. As a matter of fact, that is actually what helps us to identify a homogeneous footing. The first part that I said that either one of dx or dy or both of them, right, have variables added or subtracted. That is something that we usually notice when dealing with homogeneous equation problems. Yeah, the equations, they'll be seen in such a way that somewhere, either in the dx part or in the dy part, you would see the variables x and y being added or subtracted. Okay, you definitely must see something like that. Either in the dx part, you see x and y being added, or in the dy part, you see x and y being added, or it is possible that both of them, x and y, in the dx and dy part, they are being added. We see something of that kind when we are exposed to a homogeneous further problem. However, this is not a key reason to identify a homogeneous further problem. The main thing as the key that you use to unlock and identify that a particular ordinary differential equation problem given is homogeneous footing. That key that you use to identify it is the fact that the degree in dx and dy are equal. What does that mean? If you look at the dx part, the degree of the variables, and then the dy part, the degree of the variables, they are the same. So if in the dx part the degree of the variable is 2, we expect that in the dy part the degrees of the variable will also be 2. Such happens, then we say that the equation is a homogeneous first order ordinary differential equation. I hope that makes sense, right? This is how we identify a homogeneous first order ordinary differential equation. I have underlined this for you because that's where the main thing is based on. I just have to write this so that at least first hand, before you even start thinking of degree in the x and the y part, you would have to check first that there is a part either in the dx part or in the dy part where the x and y variables are being added or subtracted. You must see something like that. All right, so I've given you the key to identifying a homogeneous first order ordinary differential equation. I know you might be wondering, what does this really mean? Don't worry, one will pick examples to find out whether these differential equations are homogeneous or not. You would get to understand this statement, this short note, even much more better. I hope you're following the class, right? Remember, once you join the class, you can share the link to this video, this live class, to your friends. All right? You can share it to your friends so that they can benefit from this class. Get ready as we pick examples to find out the ones that are homogeneous and the ones that are not homogeneous. Once you connect to the class, please give a like, okay, to the live class. Like this video, and then share the link to your friends. Like I said, okay. You can tell us where you are watching from, where you are learning from. From where are you connected to this class? That would be appreciated. So it is time we are moving on straight to look at these examples. I'm going to write a differential equation on the board, and then we shall identify whether that differential equation is a homogeneous footing or not. Question 1. show that the DE, so we have this x plus y, then dx plus x dy equal to 0 is homogeneous. Homogeneous. So we have to show homogeneous. Okay. So we have to show whether the differential equation you have on the board is homogeneous. We have to show. So it's a form of proving. It's a form of proving that this equation you have there on the board is homogeneous. Oyebo Desire, you're welcome to join the class from VETSI. I don't think I know there anyway, or I don't think I've heard of VETSI before. But you're highly welcome. We are all humans in a global world, so it doesn't matter from where you're joining the class. I just want to know, even though I don't know the name of the place, it's okay, but you can still give further guidelines for me to get to know, particularly perhaps the country. Is it Vietnam that you're trying to indicate? I don't know, it's possible. Anyway, all the same, let's move on. So we have to show that the differential equation we have here is what? Homogeneous. So it's likely that the examiner is telling us that this is homogeneous. Now you prove it. Okay? It is homogeneous. Fine. Prove it that this equation is homogeneous. So how can we show that this equation is actually homogeneous? First of all, observe that this differential equation given to us, you see that there is a place where the x and the y variable are being added. And that happened in the x part. In the y part, there is no addition or subtraction of x and y variable, nothing like that. But at least we saw it in that dx part. That is why I said either one of the differential coefficients or both of them will have these two variables added or subtracted. It happens here. It happened here. However, like I told you, that you see x and y variable being added is not sufficient enough. It's not sufficient enough to conclude that the differential equation is homogeneous. It's not. What we prove finally that the differential equation is homogeneous or not is you checking the degree of the dx and dy part. Like I said, the degree in the x and the y must be equal before you can conclude that yes, the differential equation is what? Homogeneous. So how do we achieve that? Come along with me as we play around this together. Remember, this is GMAETS 41, committed to ensuring that our scholars get the best in their studies, to ensuring that you understand these stuffs you're studying. Are you following right? Making them 1 + 1 for you. Now, we shall look at this differential equation given to us. This is x plus y and then dx plus x dy equal to 0. My interest now is to test for this second condition, which is the key thing to identifying whether a differential equation is homogeneous or not. So we are going to select, if you want to prove it, you select, a constant. This constant is arbitrary, which means you are the one to decide it. So what you're going to use the constant to do is to multiply each of the variables there. All right. When I am done showing you the proof, I will still show you, the super shortcut to actually looking at the differential equation. By inspecting, you can just conclude whether it is homogeneous or not. Like I know very well that this is homogeneous, and I'm going to tell you, this is a homogeneous phoebe of degree 1. The dx part has degree 1, the dy part has degree 1. So the degrees are equal, and it's 1, like I said. So this is actually a homogeneous first order ordinary differential equation. Come along with me, let us get this done. We are going to use a constant, using a constant, say lambda. I am using lambda. We are assuming the constant to be lambda, okay? Now, what are we going to do with the lambda? We shall use the lambda, like I said, to multiply each of the variables. So we come to the dx part. It is going to be lambda times x, you can see that, then plus the y, lambda times y. Then this is going to be in bracket, and then dx, plus you move on to the dy part, multiply that variable there, x, by lambda, dy, and then equate to 0. This is good. I hope this has not cut off. Let me check that it is within range. Okay, they didn't go off. But I think, let me adjust the camera a little bit. Let me adjust the camera a little bit. Okay. So I guess we can go this way, right? Something. Why did you delete your message? Deleted what you dropped. Okay, we are moving on. Now that I've multiplied each of the variables here by the chosen constant lambda, we are now going to simplify that lambda and see what happens. What is common to this part? What is common to these two guys? You'll agree with me that lambda is common, so we factorize that lambda. We're going to pull out that lambda. You see, what I did is simple. Use lambda to multiply this. Use lambda to multiply this. But you want to take note of something, that when you are using that, arbitrary constant you choose to do that multiplication, that arbitrary constant must multiply each of the variable. That is the principle of proving it. Okay? So I am factorizing that lambda out so that you have x plus y dx, and then plus here also you have lambda in the dy part. So we have something like this, lambda, and then x times dy equal to 0. Now observe the lambda we have in the dx part. Observe the lambda we have in the dy part. Notice that, the degree of lambda, that constant in dx and dy is equal, which is 1. Therefore, that given differential equation x plus y dx then plus x dy equal to 0 is homogeneous. If the examiner is homogeneous first order ordinary differential equation, if the examiner asks you to state the degree, because said you can see the degree there is degree 1. How do we know that the degree is 1? You can see the power of this lambda here is 1. The power of lambda is what? 1. Degree of something with respect to polynomial is the highest power of the term there. It could be the variable or whatever. So we are interested in the degree of the constant we use to multiply. So the degree is 1 because it is power 1, as you can see there. Okay. Miss Oma Esther, welcome to GMAETS 41 Platinum level. Thank you for becoming a channel member, supporting this channel. GMAETS 41, appreciate that a lot. And you can be 100% certain of something. As you follow up with our classes for the courses that you need, your A is super setting. As you go in there, blast the course, get us the A splashes, which GMAETS 41 is known for, with first class in view. Once again, thank you and welcome to joining the GMAETS 41's channel member family. So I have shown you how you can prove that the differential equation is homogeneous, and of course, find out the degree. It's simple. In fact, if I don't want to do all this is just waste of time. It's a waste of time. Are you following, right? When you're in the examination hall, looking at a particular differential equation, you can tell that it is homogeneous as fast can be. How do you do that? Come to this part, ask yourself, what is the power of this variable x? And you'll agree with me that the power is 1. Now you have plus here. Come to this y. Ask yourself, what is the power of y there? You agree again that the power is 1. Now, because you have plus here, you use the idea of our normal mathematics principle. Okay? You can just ask yourself, what is common to this and common to this? Because under plus and minus, what we usually do is to factorize. If I give you something like 2x plus, let's say 2y, under this plus, or even if it is minus, either plus or minus, you factorize the common term. That's what you do. You factorize the common term. So if you look at the power here is 1, the power here is 1, we can ask ourselves, what is the common power? The common power to these two variables is 1, simply meaning that the dx part, the degree is 1. Come to the dy part, the only variable you have there is x. What is the power of that x? Again, it is 1. So the dy part, the degree is also 1. And so you've concluded, finding out truly that this is a homogeneous first order ordinary differential equation, because the degree in the dx part together is 1. The degree in the dy part is also 1. Let us move on to take another question. Okay, you can just imagine if you have a problem where x and y are being multiplied. Now, how can you prove it? And how can you use this super shortcut approach I've just used to identify that this thing is homogeneous? How can you use that super shortcut knowledge to actually find that out? Let us move on to the next question. Please, like I said, once you join the class, do good. Do good. Share the link to this class to your WhatsApp group, departmental WhatsApp group. Invite your friends to join. Share it to your friends, your classmates. They need this. They need this. Let me just be honest. Out of my own humanity, yeah, I've always said that. I'm out here on this space in this world now to give the best I can to humanity as much as I can, both academically and spiritually in terms of the truth about God. Okay, of course, that is even one of my major work, preaching the truth from the Bible about our God and helper, Jehovah. You know, he has always been the GMAETS 41's strength. Then, of course, in the second part of my work, secularly, is this education stuff. I don't joke with teaching. The blood that flows through me is teaching. I love teaching. I'm a teacher. Even though I studied chemical engineering, you know, but I love teaching. I love teaching. Whenever I impart this knowledge to friends and I see them smile. For example, first class results have been raining towards into the GMAETS 41. There are many of our the GMAETS 41 students, those in 200 level and during their 100 level, that have sent in their results, and you see first class, boom. No one can deny it. No one can take it away from you because you did what was necessary. Like I've always said, you will go in there, blast the exam, get that A splashes, and then look out for first class. Make sure you always do the needful. And of course, no one can take away your success. That is it. But you have to work for it. We are looking at question number 2. Question number 2. Let us see how we can find out whether this is a homogeneous equation or not. So I have got this. Show whether the DE, show whether the DE y squared dx plus open bracket x squared minus xy dy equal to 0 is homogeneous or not. Is homogeneous or not? So that's the question. We have to show whether the differential equation you have on the board there is homogeneous or not. Interesting, right? It's simple to always show that. It's simple to always show that. Like I said, do good to your friends, okay? Like I'm doing good to you. Share the link to this live class to your friends, your departmental WhatsApp group. Invite them to join the class. Like what I was trying to say earlier, you know, I just thought it like that, but let me just say, most times when ODE are being taught in classes, in lecture halls, out of 100%, I can tell you that not up to 50% are able to interpret and impart the knowledge effectively. And so many students still, at the end of taking lectures on ODE, end up complaining that they still do not understand what is there. But GMAETS 41 will always maintain that ODE is 1 plus 1. Yeah, just understand it, and that's it. It's 1 plus 1. And here on this platform, this is one such platform amongst others, right? That would give you the very best and break down the concept of ordinary differential equation for you. For example, in Unity, there is this acronym, a term used for it, Odiegu. Odiegu in Igbo means, ODE, Odiegu. In Igbo language, it means it is scary. Yeah, people get scared about this course, but hey, GMAT will tell you that this course ODE is ODZ. I converted from what many persons think of it as per Odiegu, it is scary. I convert it to ODZ, meaning it is very simple, it is easy to handle. So make sure you always stay tuned, please. I'm going to help you. By God's grace, I will really help you. Okay? So we have y squared dx plus open bracket x squared minus xy dy equal to 0. I must tell you that this is a homogeneous first order ordinary differential equation of degree 2. Yes. And it's simple. You want to prove it? You prove in this way. You want to inspect and then conclude that it is homogeneous or not. You can do that. Here, the dx part, you can see you have only one variable and it is having the power 2. And then here, in the dy part, you have these terms, x squared and then xy. What would you do? This x squared part, the power of the x there is 2. This x and y, the mathematical sign between them is times, x times y. So you just simply go ahead to say this is x raised to power 1 times y raised to power 1. Because of this multiplication, you will do something that ordinarily, it doesn't follow that principle we apply here. But you remember, it's just like a super shortcut that works in every case. And so if it does work, why can't we use it? Even if it does not agree fully with, the mathematical process that I am adopting to interpret what happens here. Like in this case, x raised to power 1 times y raised to power 1. Since you have multiplication there, you apply multiplication law of indices, where you are expected to add their powers. X power 1, y power 1. If you add their powers, you get 2. Which means that this xy part, the degree, the power is also 2. And the power here is 2. You have minus here. So you ask yourself, what is the common power of these two terms? And the common power of this x squared part and this xy part, the power that they have the same there is 2. You conclude that the dy part is power 2, and then the dx part, you can see that power 2. So it is homogeneous of degree 2. I have done something here. I told you x raised to power 1, y raised to power 1, add their powers. Since the x and y are being multiplied, add their powers and you get degree 2 there. And then somebody will wonder, what on earth, right? Why should GMAT do that? Because we know that before you add the powers of, a given base, the bases must be the same. X and y here are of different base. That principle I adopted from multiplication law of indices does not agree with different bases. If you have different bases, you don't add their powers when you're multiplying the base. But I did it here, and it worked. But I'm going to show you when we prove that actually it is not the power of x and y I added directly. It is the power of the constant which you're going to use in multiplying that I actually added. So come along and then you see as I solve it. Once again, let us use, the constant. Using the constant. Using a constant, say lambda. I am saying that I'm using lambda. Somebody can use any other alphabet. You can use K. You can use R. The choice is yours. So we're going to use the lambda to multiply this term. So that is going to be lambda times y squared. Okay, lambda times y. Use the lambda to multiply that y as a variable alone. That y is raised to power 2. Therefore, you're going to square that term. You see what I did? I used the constant to multiply the variable only. Now that variable is raised to power 2. Therefore, that 2 will also affect that lambda. So you have lambda times y in bracket, you square it. That's the principle, okay? Because the idea here is that the constant is sharing the property of that variable. So anything that affects that variable must also affect that constant. Plus, come to this, open bracket. This is x multiplied by that lambda. You notice that that x is raised to power 2. Therefore, you are going to raise this whole term to power what? 2. You are going to raise it to power 2. That's what you do here. You're going to raise it to power 2 because that x is power 2. After this x, you have minus. You are using lambda to multiply x and also to multiply y. Remember from question number 1, I told you when you're using the lambda, the constant, to multiply, it is meant to multiply each of the variables. So this is going to be lambda times x multiplied by lambda times y. Let me use the other shade of marker to write the variables, while we use another shade to write the lambda. Okay, so we've got something like this. This part has the x in it, please. This part. So I'm going to write the x, then plus this whole thing now has the y. So I'm going to enclose this in bracket because this part is for the x squared minus this part is for this xy. Multiply it by dy and then equate to 0. So look at what I've done there. It's simple. Choose a constant. The constant you use is your choice. It's not compulsory. You must use lambda. Choose any constant you want. Use the constant to multiply each of the variables. So you multiply. If the variable has a power, the power will also affect that constant. That's it. Then do your simplification. From here, you notice that we have lambda squared, y squared times dx. This power distributes over lambda times y. Remember that power distributes over multiplication and division. So I've distributed this power to this lambda and y. Then the next is plus open bracket. Here is going to be lambda squared x squared. This power will be distributed to lambda times x. And then minus lambda x times this dot is times. Okay? Lambda x times lambda y. Lambda times lambda will give you square lambda. Then x times y will give you xy. Multiply this by dy and equate to 0. I hope this has not cut off. All right, so what is common to these parts? Here you have lambda squared. I'm going to write lambda squared here. Then I'm going to put y squared in brackets, separating the variable now to what we have initially. Then get out what is common. This is lambda squared here, and this term also has lambda squared. This is minus, so you factorize the lambda squared. Remember I told you when I was showing you that super shortcut approach, I told you that actually what made me add the powers of x and y is not because of this x and y, because the bases are different. Adopting multiplication law of indices, you shouldn't or you cannot add the power of x and y here. But the reason I had to do that is I already know that what I am adding its power is actually the lambda that is the same. So you have the same basis. Multiply lambda by lambda, pick one of the lambdas and then add the powers. This is power 1. If you add, you're going to get power 2. So the lambda here has power 2. Open bracket and then write the original variable, which is x squared. If you factorize this lambda squared, you'll be left with x squared minus xy. Then dy equal to 0. Now, what did you notice? Observe this. In the dx part, the lambda came out with power 2. In the dy part, the lambda came out with power 2. So we can conclude that the equation given to us, therefore, y squared dx plus open bracket x squared minus xy dy equal to 0 is a homogeneous footing. First order ordinary differential equation of degree 2. Good. And let me tell you something. As long as you've been able to establish and identify that a particular differential equation is homogeneous of first order, the next is to start solving. Because generally your examiner will definitely ask you to solve a particular homogeneous first order ordinary differential equation. You must solve when you are seated for an ODE examination. All right, we are done answering the second question. You can see clearly that you don't even need to go through all this stress of the thing. Because in exam, let's assume you are seated for examination. You are seated for a CBT, computer-based test, or OMR sheet. You answer on paper, but it is objective. Here you have options. To identify that a particular differential equation is homogeneous, you don't need to do all this proof. You can use the super shortcut approach by inspection. Apply that knowledge I've applied here to prove that the guy is homogeneous or not. Let's take one more question to establish whether it is homogeneous or not. But this is what I'm going to do. I'll write two differential equations. I'm going to tell you that one will be homogeneous, the other will not be homogeneous. Then we are going to use the super shortcut approach just by inspection to identify the one that is homogeneous. Because I'm trying to check that the network is not disturbing. That's good. We're going to inspect and tell the one that is homogeneous and the one that is not homogeneous. Then I'll go ahead and prove why that which we say is homogeneous, why it is actually homogeneous. Please finish up. I'm going to wipe this part of the board as we pick our last question on identifying a homogeneous footing. All right. So this is going to be the next question. This is going to be the next question. Question number 3. We'll change this marker. The question is, which is homogeneous? Which is homogeneous? Which of the DE? Which of the DE? Because let's specify that it is a differential equation. Which of the DE is homogeneous? Homogeneous. So I'm going to have this A. So I shall give you this particular guy. X cubed minus 2xy, then dx plus xy squared dy equal to 0. B, x cubed minus 2x y squared 2xy squared dx plus xy cubed xy squared rather dy equal to 0. Then let me add up this one. Let me add this x dy dx and then plus y plus exponential minus x over y equal to 0. Okay. X dy dx plus y plus exponential minus x over y equal to 0. All right, so our interest is to find the one that is homogeneous and the one that is not. You know, I thought of giving you just only two differential equations, but while I was writing on the board, you know, my brain was just give them more, okay? Make it a bit complex. Trouble them. Okay, so I've given you 3 options here. Let us find out the one that is or are. So let me put is or are here because of what I've done on the board. Is / are homogeneous. Okay, so quickly we're going to do this by inspection. I hope this did not cut off. I hope it did not cut off. If it did, so that I can adjust. Let me adjust the camera a bit. Remember, we are trying to show or find out which of the differential equation is homogeneous and which one is not. That is our aim. We are going to quickly inspect the one that is homogeneous, right? Then this is what I'm going to do. I'll show that that one is actually homogeneous. And then the one that is not homogeneous will also prove it that it is not homogeneous. So that's what we're going to do. Quickly, let's look at this A. In this A part, you see clearly that this is x cubed. This x here has power 3. If you come to this xy, the variable x is power 1. The variable y is power 1. Both of them are being multiplied. You don't have any business with the constant multiplier there. When you are proving whether it is homogeneous or not, you don't use the constant multiplier to do anything. So this is xy. X is power 1. Y is power 1. If you add the powers, you get 2. Just like what we did in this question number 2. Now, my dear friends, you see, this is x raised to power 3. This is xy. The power here, the degree of these guys together, if you add them, you get 2. So if here is 3 and here is 2, there is no way you can say that the powers are common. You cannot factorize out the common power. It's not done. This is power 3, this is power 2. Different. Automatically, this dx part already proves that this option A is not a homogeneous differential equation. Yes, if you come to this dy part, yeah, this is x, this is y, you are multiplying them, add the powers, 1 plus 2 will give you 3. The dy part is degree 3. The dx part does not have a defined degree because this x here is raised to power 3, this part here is raised to power 2. Assuming this xy, maybe something happened to read that it is power 3. Let's assume that this is x squared y or xy squared. If you add the powers, you get 3. You can now conclude that this x cube and this part, they have a common power 3. You factorize the power 3 out because of this minus. And then conclude that the dx part is power 3, degree 3. Then dy part clearly is also degree 3. You can now conclude that this is homogeneous. However, that did not happen. This xy here, if you add their powers, 1 plus 1, you get 2. Here is telling you that it's degree 2 here. Here is telling you it's degree 3. It doesn't make sense. Therefore, the dx part does not have a defined degree. And hence, option A is not a homogeneous equation. It's not a homogeneous differential equation. It's not. So take note of that. Take note of that. Now we've been able to handle that it is not. Now look at this B. Let's show whether it is homogeneous or not. And I know likely that you are working on it already. So agree with me that it is homogeneous or not. I don't know. How about somebody type something about it to indicate whether it is homogeneous or not? How about someone type something about it? You can quickly inspect. This is power 3. What happens here? Work it out. What happens here? Work it out. And you can type to indicate whether it is degree 3 or degree 2, whether it is homogeneous or not. So work on that as I highlight this on the board. Okay? Has anyone typed something? Let me check. There is a comment indicating whether option B is homogeneous or not. Indicating whether option B, x cubed minus 2xy squared in bracket dx plus xy squared dy equal to 0, is it homogeneous or not? That's good. So it is homogeneous. It is homogeneous of degree 3. And you can see that for yourself. This is x raised to power 3. If you come to this part, this is x raised to power 1. Add it to y raised to power 2. If you add it, 1 plus 2, you will get 3. So this part is degree 3. This part is degree 3. You have minus, so you factorize the common degree, which is degree 3. Telling us that the x part has degree 3. And then xy squared dy, this xy, 1 plus 2 is going to give you 3. So this is also degree 3. The dy part is degree 3. We can now conclude, since the dx part is degree 3, the dy part is degree 3, then B is actually what? Homogeneous of degree 3. Answer. A is not. Option A is not homogeneous. So x cubed minus 2xy dx plus xy squared dy equal to 0 is not homogeneous. Take note. I've said the reason for that. We have also explained that this guy is homogeneous. This is A. This is A. B is homogeneous. So I will indicate B. Now let's prove that this is not homogeneous before we look at B. Okay, Let's identify them before I prove. B, I've explained that this is homogeneous of degree 3 already, so I'm going to write x cubed minus 2xy squared, and then dx plus xy squared dy equal to 0 is homogeneous. Homogeneous of degree 3. Then C. Let us analyze C and C. This C you are seeing here is x dy over dx, that's x dy dx plus y plus exponential minus x over y equal to 0. Now when you are dealing with this, you see you can do something like clearing fraction. Yeah, so as to separate the dy from the x. You can do something like clearing fraction. This is what I mean. Having x dy, then this dx we multiply this y, this dx we multiply this exponential minus x over y, which simply means that we can rewrite this as plus y plus exponential minus x over y, all in brackets dx, then equal to 0. So this equation you are saying is the same as this equation. Does that make sense? So you have that in mind as I analyze. So this part, y and this exponential term are being added. Clearly, you can see that this dy part, look at it, x is raised to the power 1. So the dy part has degree 1. The dy part has what? Degree 1. What about the dx part? Let's analyze. This is degree 1. This y here is degree 1. Okay? Let us find out what the degree of this exponential part will be. X you are seeing here has power 1. Y you are seeing here has power 1. So you can see it's power 1, but observe something now. This whole term, let's see what can happen to it. If you simplify, it's going to disappear to leave you only with y. How true is that? This is x raised to power 1 all over y raised to power 1. Applying indices law, division law of indices. If I have x to the power of 1 divided by y to the power of 1, if you pick one of the base and subtract the powers, division law of indices, you will get 1 minus 1, which is equal to 0. Which means that this is exponential minus 0. Minus 0 is the same as 0. Exponential 0 will give you 1. Exponential 0 will give you what? 1. So you see this becomes a constant. Therefore, you locate this. This is y. And y alone here is raised to power 1. Making all these terms you have here to be degree 1. That is the dx part to be degree 1. You see already that the dy part is also degree 1. So this is actually a homogeneous equation of degree 1. Remember what I explained here. This is x raised to power 1 over y raised to power 1. Just the same as we handled this guy when we added the powers, because you're multiplying the variables. Here, as you're dividing the variable, you adopt division law of indices, where you will subtract the powers. 1 minus 1 will give you 0. So you have exponential 0, which is 1. So this whole guy becomes a constant. And I told you, when you are checking the degree of this guy, you have no business with that constant. You'll be left with y. This y alone has power 1, which exists, which survived here, telling us that the dx part is degree 1. And the dy part, you can see clearly, is also degree 1. So option C, or the differential equation given as C here, is a homogeneous differential equation of degree 1. So I'm going to write it. X dy dx plus y plus exponential minus x over y equal to 0 is homogeneous. Is homogeneous of degree 1. Of degree 1. So we've been able to, highlight these guys as to which is homogeneous and which one is not homogeneous. I've explained to you why this is not homogeneous. Just a quick proof as per solving it on the board for you to see. Okay, but it's no longer really necessary. I just want to tidy that up, and then you see why it is not homogeneous. Then on your own, you can work on the other guys why it is homogeneous. I already explained that already. Okay, so what do we have here? Let's see what we have here. I'm trying to check this function. I think this function has something multiplying it. Permit me to quickly check, please. That function, that exponential term, seems to have something multiplying it. Guess I thought as much. It has x multiplying it. Because there's no way this will just disappear like that. There's no way this will just disappear and become a constant. Having just a constant, there is no term you can factorize from both of them. Okay, so there is x here. So x times exponential that. Y plus, I'm sorry for omitting that earlier. And good enough, based on the classical knowledge of ODE, I was looking at it and said, there is no way you can just have this degree 1 alone without having something to factorize from here to have the same degree. So the exponential part here has degree 1 because this guy has already disappeared, to give you 0 exponential 0 times x, which gave us what? X. So the x here has power 1, the y here has power 1, so the dx part again still has power 1. So nothing changes in terms of the fact that it is homogeneous. Yes, it is, and the degree is 1. So let us prove. Let us do the proofs, please. I'm going to do 1 and C. I'm going to do 1 and C. I'm going to do 1 and C, or A and C. For the A, we have x cubed minus 2xy, then dx plus xy squared dy equal to 0. What made us say that this is not homogeneous? Use the lambda and multiply each of the terms there. So we'll come here, lambda times x, raised to the power of 3. This is a waste of time. I could have just simply done lambda cube x cube. We don't have time. This is meant to be a 1-hour class, I guess. So let's just go straight. No time. So lambda times x will give you lambda x, then all raised to the power 3. Distribute the power 3. So you have lambda cube x cube minus 2 times lambda. 2 times lambda x times lambda y, because the lambda will multiply each of the variables there. So this whole term bears the x. Then plus, come to this, lambda times x, and then times this y has squared. So it's going to be lambda squared, y squared. All this term is dx, then equal to 0. I don't know if he has cut off, but I hope it is still within range there, okay? Equal to 0. So from here, you notice that if you multiply this, you're going to have lambda squared. Okay, so this is going to give us lambda cube x cube minus 2. Lambda times lambda is going to produce lambda squared. Then x times y will give us xy. Then you have your dx here. Then plus lambda times lambda squared is going to give us lambda cube. X times y squared retains our xy squared as given from the question. This is dy equal to 0. Now we can now do our factorization. This term and this term, in terms of the lambda, what is common to both of them? This is lambda raised to power 3, this lambda raised to power 2. The common term here as lambda is lambda squared, because inside this lambda cube, you have lambda squared. Pull out the lambda square, which is common, open the bracket, and then you are left with lambda x cubed minus 2xy dx. Remember, you pulled out lambda raised to power 2 from these two terms, factorization. This is minus, so you have to factorize. From here, you pull out lambda cube. One of the lambda will be left to multiply x cube. Look at it. Then from there, you pull out lambda cube. There will be no lambda cube there again. Then come to this term. You see clearly that you have lambda there. So this is going to be plus lambda raised to power 3. That's the only lambda you have here. Lambda cube. Okay, so lambda cube is what you have in this dy part. That's what you have in this dy part. So if you check, you would see that the degrees are different. Different degrees in dx and dy. Hence, not homogeneous. So that is it. Remember, I will say for it to be homogeneous, the degrees in dx and dy must be what? The same, must be equal. All right, so let us look at C. You can work on B. You can work on B yourself, okay? This is A, proven already that it is not homogeneous. So I'm going to jump to C. You can work on B. We've done a lot of things on that in question 1 and 2 already. So the C part is x, dy, dx, and then plus y, x exponential, plus y plus x exponential minus x over y, then equal to 0. Like I said, if you like, you can just clear the fraction. To achieve that, you have x dy, then plus all these 10. Dx will multiply this, dx will also multiply this. So dx is common to y and x exponential minus x over y. So you can pull out the dy and then enclose y plus x exponential minus x over y in bracket dx equal to 0. Use your lambda to multiply. Lambda times x dy plus, come over here, lambda times y, and then we've got plus lambda times x, then exponential minus, come over to this power, this is going to be lambda times x in the numerator of the power over lambda times y, that's going to be equal to 0, dx equal to 0. Dx equal to, let me see if the camera still catches up that part. I think I've got to do a little adjustment also. Good. So I've multiplied each of the variables by lambda, and you agree with me that here this lambda will cancel out. This lambda will go off with this lambda. If it goes off, this term and this term has lambda common to it in this bracket because this lambda is multiplying this. This is going to be lambda here, okay, and then x dy. Plus this part, this is lambda y plus lambda x exponential minus x over y. Lambda in this y part, lambda in this part of x exponential. So lambda is common because of this plus, you factorize it out. So this is going to be the lambda, then open bracket, you have y plus x exponential minus x over y, which is the original function dx equal to 0. So you see that the degrees here are the same. This is degree 1, this is degree 1. Therefore, we conclude that this differential equation C is a homogeneous equation of degree 1. So I can now say hence homogeneous of degree 1. So having said this, you have identified that this guy is homogeneous. You can now solve if you're asked to solve it. So guys, we are done with how to identify a homogeneous first order ordinary differential equation. I have to spend time on this. It's not as if it's necessary, because plus minus, when you come to real exam situation in terms of CBT, especially for the school that I'm connected to, where I run tutorials also and where I belong to, Unizik, I know that they are my 202 ordinary differential equation in CBT. So you will go through all these things in terms of the exam. Your lecturers might do one or two things about it, but for your exam is not necessary. Because CBT, except perhaps before the exam day, they decide to change it to theory. Fine and good. Then you want to prepare for something like this. However, for all the friends that are connecting from different schools and all the parts of the world, if you're taking theory, you can't avoid this. An examiner has the right and can and will ask you a question of this form. Prove that this guy is homogeneous or not, and then state the degree of that equation. Can be asked that. So this is what you do. And I hope I've been able to deliver this effectively. Of course, as always, from the GMAETS 41. We are going to conclude as I give you the transformation that is now used to solve this equation. Because once you are able to determine that a particular differential equation is homogeneous, the next thing is to solve it. Find the solution of that equation. Get the general solution. If the examiner wants to get a particular solution, the question will state it. Obtain the particular solution of this. They will give you the initial value problem, IVP or BVP, boundary value problem. Okay, that's the initial conditions to be given. So how do you now solve? How do you solve a given homogeneous first order differential equation? Can screenshot this, this is cool, so that I'll wipe this part of the board and then write the transformation you use in solving this equation. All right, I'm going to wipe this. Remember, at the end of this class, a copy of this live class will be made available. Therefore, you can come back and do what? Copy your notes right? If you so wish. Of course, it's necessary. Transformation of solving homogeneous footing. Homogeneous footing. So I want to find out the transformation you use. And the transformation is y equal to ux. Some can use vx. It doesn't matter. Whether you use ux or you use vx as a transformation, it doesn't matter. Now, once you get this transformation, we have the general method of solving this. However, from the GMAETS 41, I am going to expose you to the Omaka's FD over Fn method of solving homogeneous footing. You will love it. Remember, whatever I decide to adopt anytime or to bring out as a method, I had already published this approach to solving homogeneous first order ordinary differential equation. On this channel, if you go to the playlist, all right, scroll and locate Math 202 playlist, click on it, and the videos available opens the display, and then you scroll to check. You would see a particular video where I published the Omaka's FD over Fn method of solving homogeneous footing. One of the fastest method of reducing a homogeneous first order ordinary differential equation to separable variable equation before you can actually do your integration. Because this type of ODE, this type 3, you have to first reduce it, change it to separable variable equation. That is, you change the homogeneous to separable variable before you can integrate. So in the general method, you use this transformation. But by the Omaka's FD over Fn method, although this transformation will come at the end, but what you use is y equal to u. Y equal to u, that's what you use, because you're going to cancel consciously all x from the equation. Now, if I'm to solve this equation now, what I have to do first is to cancel all the x that I have there. How do you cancel? That is divide. Divide each of the x by itself. So here you divide x by x, you get 1. Here you divide x by x, you get 1. 1 times the exponential will give you the exponential gap. Then you apply the Omaka's FD over Fn formula of solving it. But don't worry, like I said, in our next class, we're going to say this. But just have it in mind that the general transformation is this. Even if you use the Omaka's approach to it, towards the end, you will still apply this transformation to be able to bring back your x and y in the solution. All right? So have this in mind. That's the transformation, standard transformation used. Okay, so by the general method. Now I'm going to write notes. Notes. Using Omaka's FD of u over Fn of u formula. A homogeneous equation. A homogeneous equation is solved using integral FD of u all over Fn of u minus u times FD of u. I'm giving you this formula. Make sure you memorize this formula before the next class. Du equal to integral 1 over x dx. This is the separable variable equation form of any homogeneous equation. This is the separable variable equation form of any homogeneous equation. Okay, I said I published this, I think, I've published it in the public domain online. Yeah, online here, yeah, because this is on the channel where I bring out things for you friends, okay, at least the things that God has blessed me with to be able to develop in terms of mathematical works in my own little way. Good. So we're going to see how you apply this formula to deal with any homogeneous footing problem. You will love this, like I said, and you hardly would see this anywhere. Yeah, you hardly would see this. So make sure you tune in and learn this thing, because in your exam, this is really what you would have to need to use in order to be fast to reduce any homogeneous equation to separable variable so that you can solve. If you go through the general method, the process might be tedious. For those that are sitting for CBT exam, it will be difficult, to be able to beat up time within the framework. That is why, of course, over time, I've worked hard to come up with this. Thank you for tuning in, and do have a wonderful time. I'll be seeing you, by God's willing, next week on Wednesday. But remember, I can just come up anytime to take you on anything regarding ODE. It is true that the class is scheduled every Wednesday, but before the next Wednesday, I can just host any class and do something. So what would you do in order not to miss out in the class? Make sure you are subscribed to this channel. Make sure you turn on the notification bell and select all. Subscription and turning on notification bell, selecting all, these are free of charge. You're not charging anything, so do it to help yourself. Are you following right? Then go ahead, as much as you can, please support this channel by becoming a channel member on the platinum level or diamond level. The higher the level, the more benefits you get. Is that okay? However, in either way, the platinum level is sufficient. It's sufficient. Okay, don't go for the diamond. Don't go for the gold level. Go for platinum and or diamond level. Okay, and I will greatly appreciate. This will help you to get access to all key lecture videos on ODE and other courses on this channel. Once you apply for the platinum level, you get access to as much as 90 to 95% of the video lessons here. That's all of them. Yeah, all of them. All right, so I'll be seeing you, like I said, in our next class. Do have a wonderful time.